Have you ever typed a command like ls into your terminal, hit enter, and just wondered, how does that actually work? I mean, it feels like magic, right? But it's not. It's this really fascinating dance of requests to the operating system, these things called system calls. In this explainer, we're going to pull back that curtain and show you exactly what's happening under the hood.
Seriously, it's something so many of us do 100 times a day. You type a command, you press enter, and boom, the program runs. It feels instantaneous. But what's the real journey? What happens in that split second between your finger hitting the key and the output appearing on your screen? That's the mystery we're going to unravel today.
All right, so the very first thing your shell has to do is create a new worker to handle your request. See, the shell can't just stop being a shell to become ls. It has a job to do, so it needs to delegate. And that whole process kicks off with the creation of a brand new process. And how does it do this? With a super important system call called fork. Honestly, the best way to think about fork is like a photocopy machine for processes. When your shell calls fork, the operating system makes a nearly identical clone of it. This new clone is called the child process, and the original shell becomes the parent process.
So the sequence is pretty simple. Our parent shell is just chillin', waiting for a command. It gets one, it calls fork dot, and the OS creates a perfect duplicate. So now we have two processes, but, and this is the crucial part, at this exact moment, that new child process is still a shell. It's a perfect clone, remember? It has no idea how to list files. It needs a transformation, a serious makeover.
So that brings us to the big question, right? If the child is just a perfect copy, how in the world does it morph into the command we actually want to run? Well, this is where this beautiful dance between inheritance and transformation comes into play.
Okay, so while they start out with the exact same code, they each get their own unique process ID, so the OS knows they're two different things. But the real magic, the secret sauce, is in that last row, open files. The child inherits all of the parent's connections to the outside world, like its connection to your keyboard and your screen. This is so important, because it's the key to controlling where our command's results actually go.
And this is the transformation step. The child process calls another system call, this time from the exec family. Now think of exec as a brain transplant. It completely rips out the process's current program, all that shellcode, and replaces it with the new program, like ls. The body, the process ID and all those inherited connections, stays exactly the same, but its brain, its entire purpose, is brand new. It is no longer a shell. It is now the ls command, ready to do its job.
Speaking of those inherited connections, let's talk about input and output. I mean, a program that can't communicate is pretty useless, right? It needs to be able to read input from somewhere and write its output somewhere else. And the cool thing is, we can control that flow of information.
By default, every single process gets 3 standard communication channels. They're identified by these little numbers called file descriptors. So 0 is for standard input, which is usually your keyboard, 1 is for standard output, which is your screen, and 2 is for standard error, also usually your screen. These are the open files we were talking about, the connections that our child process inherits directly from its parent.
But what if you want to save your output to a file instead of just printing it on the screen? Well, that's where another system call, dup2, comes in. It's amazing. Think of it like an old-school telephone switchboard operator. It lets us unplug a connection from its default spot and plug it into something totally new, like a file.
So right out of the box, file descriptor 1, our standard output, is wired straight to the terminal screen.
But here's the really clever trick. Before the child calls exec to transform, the shell first opens the file we want to write to, and then it uses dup2 to rewire the connection for standard output.
And just like that, the connection to the screen is replaced with a connection to our file. So when the child finally does exec or becomes ls, it inherits this new plumbing. The ls program itself has no idea. It's completely clueless. It just thinks it's writing to standard output, and the operating system makes sure that data flows right into the file. It's an incredibly elegant and powerful design. Okay, so our process is born. It's transformed and its communication is all set up. But once it's running, it's not just some wild thing running free. The operating system and us, the users, we have ways to watch it and control it. Almost like we're pulling the strings on a marionette.
You know, when we use a command like ps, we can see the state of every process. A process can be R for running, actively doing stuff. It can be S for sleeping, maybe waiting for you to type something, or T for stopped, which is what happens when you hit Control Z. And then there's the weird one, Z, for zombie. A zombie process sounds bad, but it's really not. It's just a child process that's finished its job, but its parent hasn't officially checked in on it yet. So it's not running, but its little entry in the system's process table hangs around for a bit. This is a crucial feature, not a bug. It lets the parent come back and ask, hey, how did it go? Did you succeed or fail? And then it can finally clean up.
So how do we actually do all this controlling? How do we stop a process with Control-Z or kill it with Control-C? How does the parent even know the child is done? The answer to all of this is a universal communication system built right into the OS called Signals.
You can think of a signal as a tiny little text message sent from one process to another, or from the operating system to a process. It's an immediate notification that something important happened. It basically taps the process on the shoulder and says, hey, drop what you're doing and deal with this right now.
And you've been using signals this whole time, even if you didn't know their names. When you smash Control-C, you're sending the SIGINT signal to interrupt and terminate a process. Control-Z, that sends SIGTSTP deposit. The kill command sends a polite request to terminate called SIGTERM, while kill-9 sends the unblockable, unstoppable SIGKILL, the ultimate off switch.
Now, what's truly amazing about this is that processes don't have to just sit there and blindly accept the default action for every signal. For most of them, they can actually rewrite the rules and decide for themselves how they want to respond.
Programs can do this using a system call called SIGAction. This lets them catch a signal and run their own custom code instead of just dying. Think about a text editor. When you try to close it, it might catch that terminate signal, not to just exit, but to first pop up a little box that asks, hey, do you want to save your changes? It's how programs can handle interruptions gracefully.
But, and there's always a but, the operating system is still the boss. It always has the final say. There are two signals that a process can never ignore or redefine: SIGKILL and SIGSTOP. This makes sure that no matter how misbehaved a process gets, the system admin always has an ultimate off switch and an ultimate pause button to maintain control. It's the system's safety net.
So there you have it. We started with a simple command and we uncovered this whole deep system of creation, transformation, communication, and control. This design really reveals a core philosophy of the operating system. It trusts programs to manage themselves gracefully, but it always keeps ultimate authority with a few unbreakable rules. And it's that elegant balance of trust and control that makes the simple act of running a command both incredibly powerful and incredibly reliable.